everyone, welcome to Learning at 11th Hour. In this video, we are going to talk about the first order RC circuit where the capacitor is initially undischarged and it is connected to a voltage source whose value is V naught. So, say the capacitor is charged from this voltage source and it happens through the resistor R as shown in this circuit diagram. In that case, how would we analyze our circuit? So initially this capacitor's voltage is 0 and then it charges and finally when both the plates are saturated with charges, that would happen when the voltage V naught and the voltage across the capacitor are equal. At that time there won't be any current flow from the voltage source to the capacitor. So after the capacitor is fully charged, the voltage across the capacitor would become V naught itself. That is the voltage of the voltage source. Now let's apply KVL to this circuit and obtain the equation. So this is the current which is flowing. I'll mark the plus and the minus and the voltage drops. And if I assume a clockwise drop direction, I can write the KVL equation as minus V naught u of t plus I into R plus V. That is the drop across the capacitor. All this put together should be equal to 0. Now, what is this u of t? So, if I am able to plot this, so this is called a step function. So, whose magnitude is V naught. So, when I plot it, this is how it should look. So, if this is the voltage, with this is the time, this is u of t, where this magnitude, the maximum magnitude of it is actually V naught. So it's going to be just a straight line parallel to the time axis with an amplitude of V naught. So this is called a step function. So V naught u of t is going to look like this. So if I'm going to apply this kind of a constant voltage of V naught to this capacitor, then it is going to get charged over a period of time and reach the value of V naught. So let me rewrite this KVL equation which we've obtained. We'll get IR plus V is equal to V naught u of t, where I can be written as C into dV by dt. So I'll replace I over here. What do I get? V plus C dV by dt into R is equal to V naught u of t. Now, if I divide this entire equation by RC, what do I get? So 1 by RC into V plus dV by dt is equal to V naught u of t by RC. The initial condition can be written as V of 0 is actually 0 because the capacitor was uncharged when it was connected to the voltage source. So this is the initial condition which needs to be considered. Now we need a solution which satisfies both of these, right? So the solution to this equation will have two parts to it. One will be called as the particular solution. So the particular solution, also known as the forced response. So the forced response in this case is going to be V P of t, P stands for particular solution, is equal to V naught. So we are forcing the capacitor to be charged to V naught as its final value. So this is the first response. Now this will satisfy this equation, but it is not going to satisfy the initial condition as such. So we need a homogeneous solution for that. So the homogeneous solution, also called as the natural response of the circuit, that is going to be represented as Vh of t and is going to be given as A into e power minus t by Rc. So this is the homogeneous solution. And when we add both of them, that will be satisfying both of these, the equation as well as the initial conditions. So then V of t therefore will be Vp of t plus Vh of t, where Vp of t is V naught, Vh of t is A e power minus t by Rc. Now we know that V of 0 is actually 0. So we can use this to find out the value of A. So 0 is equal to V naught. So I'm doing this at t is equal to 0, right? So V of 0 is 0. 0 is equal to V naught plus A e power of minus 1 0 by RC. So e power 0 is nothing but 1. So here we see that A is going to be equal to minus of V naught. So we can replace this in our equation over here. So what we get is V of t is equal to V naught minus V naught e power minus t by RC. So taking V naught common, 1 minus e power minus t by RC is going to be equal to V naught. So this is the expression for a capacitor to be charged from 0 to a final value of V naught. The expression for current can be obtained as I of t is equal to V naught by R e power minus t by RC. So that is because I is equal to C dV by dt. So when we differentiate the equation over here, this is what we get. Now let us plot V of t and I of t and find out how they look. So in case of V of t, we have the input as the step response, and our capacitor has to charge to a value of V naught, but it's not going to happen instantly. So it's going to take some time, and then it is going to reach V naught. So it will start from 0, right? So this is the response, it's going to reach V naught. But there are some important parameters which we need to know over here. So that is, let's look at this parameter called as tau, which is RC. So we know that V of t is equal to V naught 1 minus e power minus t by RC. If I replace t is equal to RC, which is nothing but the time constant tau, what do I get? V naught 1 minus e power minus 1. And we know e power minus 1 is 0.368. So what we get is V naught 1 minus 0.368. So what we get here is V naught into 6.632. So this value basically becomes about 63.2% of V naught. Now looking at the current response, what we get here is, say this is the time axis, this is the current axis. Now the the expression for current is V naught by R e power minus t by RC. So it starts from V naught by R and it discharges exponentially till it becomes 0 when the voltage of the capacitor becomes equal to the source voltage. So when the two voltages balance out, there won't be any flow of current from the source to the capacitor. So at that point it becomes 0. But when t is equal to tau, that is RC, at that time the value of current would be 0.368 times of V naught by R. Because when we replace it here, we get V naught by R e power of minus 1. So that is the value of the current at tau is equal to RC. Let's try out this simple problem to understand what we've just discussed and how we can apply it numerically. So if there is a 4 microfarad capacitor, its initial voltage V0 here is equal to 2 volts. So it's not completely uncharged. There is an initial voltage of 2 volts over here. V naught is 2 volts. And this is connected to a 12 volts battery. So V of 0 here is 2 volts, and V naught from our analysis, right? This V naught, this is actually 12 volts. And the charging happens through a resistor of 5 kilo ohms. And we need to compute the voltage across the capacitor, that is V of t, and the current through the capacitor, I of t. So v of t is given as v naught plus a e power minus t by rc. Here in this case, we cannot say that a is equal to minus v naught yet, because v of 0 is different in this case. So the value of a will differ. And here I is going to be what? The difference between the voltage of the voltage source and the capacitor. That would be the potential drop across these two terminals. That is the potential drop across the resistor. So V naught U of t and V initial. So the difference between the two divided by 5 should be I. So here, since the capacitor is involved, the current will have an exponentially decreasing trend. So finally, the expression becomes what? V naught, that is 12 minus V by R e power minus t by RC. So this is the expression for the current for this circuit. So let's try to find out the value for A. So V of 0 is given as 2 volts, which is V naught plus A e power minus 0. So 2 is equal to 12 plus A. So therefore A is equal to minus 10. Now we also need to compute the expression RC for this equation, right? So what is RC? RC is the time constant, where R is 5000 and C is 4 into 10 power of minus 6. So you have 20 milliseconds as your tau, time constant. So now we can write the expression for V of t as V naught, which is 12 plus minus 10 e power minus t by tau, where tau is 20 milliseconds, or 12 minus 10 e power minus t by tau. This is the expression for the voltage across this capacitor. Now, in the expression for current, I of t, it will be 12 minus V. V is nothing but the initial voltage across the capacitor. So 12 minus 2 by 5 kilo ohms. That is going to be the initial starting current, from where it is going to discharge exponentially till it becomes 0. So 12 minus 2 by 5 into 10 power minus 3 e power minus t by tau. So that becomes 10 by 2, which 10 by 5, which is 2 milliamps. Okay, so 2 e power minus t by tau milliamps, where tau is nothing but 20 milliseconds. So this is the time domain response of this circuit here, where tau is equal to 0.02 or 20 milliseconds, and the voltage at time is equal to tau, or the time period. The voltage value is going to be 63.2% of the maximum, which is 8.32. And over here we have the uh, current response. So when t is equal to tau, it is going to be 0.368 times of 2. 2 is V naught by R. In this case, it is going to be 12 minus V by R rather. And here, this is actually 63.2% of 12. And over a period of time, it is going to reach the value of 12 volts. That's all with today's video. I hope you've understood the concept of how a capacitor is charged through a resistor in a first order RC circuit and the interpretation of their frequency responses. Please do subscribe to this channel and keep watching 11th hour for more such videos.